Alright, hell yeah. So here's the problem if you want to pause the video. But yeah, we're going to go over this, and this is kind of like going to be a fast answer. Fast for me is like 30 minutes. But we have this frame of some sort. It's a rigid body, and we have these connections. Now, these connections can be solid, but they are pivoted. So these are pivots, and what I'm going to do is I'm going to just assume that they're all in tension. So that's the first thing that I'm going to do is put arrows on showing S1, S2, S3 are in tension. That's the only thing we don't know. We know this load is down, and we also know, it's down, the load is L, and then it's also, because of this pulley, we have that same L right there. So we have L right here and L right there. Alright, but we do know this, and it's going to act right at this pivot. I need to make a separate video of like why, even though the pulley has dimension, like why that for sure just acts right at that pivot. But anyway, this video is going to be, okay, we have three vectors. What we can do is we're going to take two of the vectors, and they have a line of action, and where they meet, so S1 and S3 is going to meet right there. And if we take moments about that point, then we're just going to have S2 as our only unknown. We know all of these forces, and we don't know S2. But we'll have one equation, one unknown, and that's going to be what we're going to do. So the first thing, I have a ruler. We're just going to draw some lines. We have, what did I say, S3 and S1. So those are the ones that I'm going to connect. Alright, heck yeah. And so we need equations for lines. And I don't know, it's like, I don't think I practiced this enough, so it was never trivial for me. But what I'm going to do is, I'm going to pick a coordinate system, and I don't even know where I should start for my coordinate system. I could just come up here and say this is 0, 0. Might as well, right? Because then my equation for S1, so I'm going to have equation S1 is going to be y. I'm not going to have any y-intercept. The general equation for a line is y is equal to mx plus b. But I'm not going to have any y-intercept if I set my coordinate up there. Now this, a few things, is that this has a slope of down 1 over 2. That's all I'm going to do for now, so I'm going to say y is equal to just the slope times x. And that's going to be rise over run, so we're going to go negative 1/2 x. Cool, alright. And then our equation for S3, well, it's vertical. And in the other video, I was like, oh yeah, well, y isn't really anything. Well, y is everything. You know, every value if x is 3, y can be any value between negative infinity to infinity. But how we categorize this is we say this is x is equal to 3. And the other thing is, like, where do you get the 3? This is in millimeters. I'm going to say 3,000 millimeters is 3 meters. I'm going to change everything to meters. So that's 2, this is 5, this is 2. 1. This is 2.5, but we're going to get an answer as a fraction. So I want to turn this 2.5 into 5/2 just to work with that. And then we have 2 right there. Okay, so we're all set there. Okay, so now I can set these two equations equal to each other. So I can put in this 3 right into this x, and I'll find that y is equal to negative 3/2. So this is my coordinate. So my coordinate for where these meet is going to be x is 3, y is negative 3/2. Alright, sweet. And maybe I'm regretting putting my coordinate system right here, because maybe I wanted it right here, because then all values of y are going to be positive. I can get over it though. We can do it. And, okay, so now what? Well, we want to take moments about this point. I'm going to call it E. And we want to draw this line in. And so this is point E. And what we want is a 90-degree angle towards towards S2. If we, yeah, and this is where I really wanted to make this, yeah, let's redo this. It's going to make my life just a lot easier. So this is going to be the origin. And so this, what did we say? So this is going to have a y-intercept. So we're going to have y is equal to this slope plus b, but it's going to be up 5/2. So this equation for S1 is going to be -1/2 plus 5/2. And then when we throw in 3 into here, we're going to have y is equal to -1/2 times 3 plus 5/2. And we're going to get -3/2 plus 5/2. And this is going to give us 2/2. Is that right? And that's going to give us, sorry, 2/2. And that's going to be 1. And so our where this is going to hit is going to be over 3 up 1. So let's make that connection change. Cool. Alright, so that was useful y. We're going to take, so this is point E. And yeah, okay, so now this is point E. What we're going to have is this horizontal distance. So now how do we find that horizontal distance? What we do is we take a line from, we need to find some sort of point on this line, and that's going to be our origin. And we're going to take a vector from B to E. Yeah, this is good just to go through it. You know, I'm not 100%, confident, but we're pretty decent. So what we have is this vector B to E. And that's just going to be over 3 up 1. Cool. And what we want is, and we can say this is a hypotenuse. You know what I mean? This is the hypotenuse. This is a right triangle. And so we want to know this portion of the right triangle. Now, one way to do it is just find this angle and then take the cosine of that. But the way to do it with the dot product is pretty cool. What we want to do is, and I'm going to kind of extend this line just a little bit. What we want to do is take this vector BE and then dot it into this vector. I'm going to say this is E prime. So we have E and E prime. So if I have a unit vector, and how do I do this? I would actually want to do it from E prime to E. It doesn't matter. You're going to get a negative number, and we'll see that in a second. But we just want this length right here by using the dot product. So the dot product, let's spell it out. Or this length right here is E prime to E. And we want the absolute value. So it is a vector. So that's a vector, but we put the absolute value sign because we just want this distance. And what's that going to be? That's going to be this vector. That's going to be the hypotenuse, BE. And we're going to, so that's a vector, but we're going to dot it with another vector. And when we dot product, when we multiply one vector dotted with another vector, we get a scalar. And that scalar is going to be that distance. So how does this work out? Well, we have to dot it with the unit vector in this direction. And when we do that, like let's say this vector is like, well, we can see it's about 3. So this vector is about, the magnitude of this is about 3. So why when we dot product, when we multiply it by a unit vector, which is only a magnitude of 1, why do we get this length, which is about like 1.5? Like why would, and one way to do this visually is take your hypotenuse. I always divide it in 2. It gives me an idea of potentially of what the shorter side is. You know what I mean? Hey, sometimes it's like, oh, hell yeah, this looks about half. So if this is about 3, this is about 1.5. Okay, hell yeah. And this is really good for me to explain, you know what I mean, just keep explaining to myself. What were we even talking about? Yeah, so this vector has a magnitude of 3. The dot product is multiplying by another number. If this vector was also 3, it would be 3 times 3 is 6. Cool, and what would that even mean? And it's a dot product, so it's you have two vectors. Maybe they're like this, and it's the cosine. It's like it's the shadow of this vector onto this vector. So if your angles are kind of like 30 degrees, like the cosine of 30 is 0.866. That's 86.6% of this vector is going to be shadowed into that one. But the dot product is still a multiplication of vectors. It's, you know what I mean? It's still taking 3 and multiplying it by 3, which would be 6. And then it would be 80% of that. You know what I mean? And then so you just get a number that maybe doesn't mean much because you just multiplied two numbers, and that's not what we want. We want to take this 3 and get something and get this 1.5. How do we do that? Is we multiply this 3 by this unit vector that's only 1. So if we multiply 3 times 1, we're going to get 3. But now we can see that, hey, this is only 80% of that 3. So in that case, and the way that we have it drawn right here is that this and I would probably not reference this angle because the angle you're probably referencing is this angle now when we do this dot product. So now I have this vector 3, and then I'm up at a 60-degree angle with this unit vector. So the shadow of this is only a half. So I have 3 times 1, but I'm only getting half of it's being useful. So that's where that 1.5 would come in. And that's how dot product works. It's the cosine component. But the take-home point is you want to multiply it by 1. I want to take 3 times 1 because then that just gets me this component of that hypotenuse. Cool. So, heck yeah. So that's going to be this vector BE dotted with... and you can't mess up. If you said the vector E prime to E or E to E prime, you're only going to be off by a negative. This is going to be a scalar, and if you just change directions, it's just going to be... one answer is going to be positive, the other answer is going to be negative. Since I'm starting at B and going this way, I want the positive number will be E prime to E going that way. So that's how I kind of visually reference that. Okay, so we're going to have this vector E prime to E. And that can be, we don't know this length actually. You know what I mean? So we have that vector, but we're going to just we're going to divide it by the magnitude of whatever that is. So that's going to be E prime to E. And this is going to be the unit vector. Well, technically, I just know what the unit vector is going to be based on geometry. So let's take a look at this. So this line right here is perpendicular to the line that we're trying to find. And this has a slope of 1 and 1. And if this is 1 and this is 1, what's the hypotenuse right here? Well, it's going to be 1 squared plus 1 squared. This is going to be the square root of 2. Now just keep in mind that this is not a unit vector. A unit vector is when your hypotenuse is 1. But how you can get, a triangle where it is a unit vector is divide everything by your hypotenuse. So I'm going to do square root of 2 divided by the square root of 2. I'm going to do 1 divided by the square root of 2 and 1 divided by the square root of 2. So I always like to say, like, hey, if I have, well, I just said this the other day. That's the first time. Second time then. So if I have a 30-degree triangle and like, and we have some sides, let's say this is just 0.86 and this is 0.5 and this is 1. Can I just add 1 to every side and get the same shape of triangle? Hell no. But can I multiply 1? Or let's say 2 now. Can I multiply, let's rephrase that. Can I add 2 to every side? No, it's going to change the shape. Can I multiply 2? Can I divide by any number? Can I multiply by any number to all sides of this triangle and still keep that proportion? And the answer is yes. So that's what we're doing here. We're just dividing every side by the hypotenuse. And so now this becomes 1. You have a hypotenuse of 1, and here's your sides. And this is a unit vector. Cool. So the other thing that we know about perpendiculars is if this was 1 over 1 up, this is going to be over 1 down 1. So that's going to be right there. And so down 1 over 1. And if we wrote this as a unit vector, because if, well, one way to write it is just do this. To be like, heck yeah, this is the representation of that slope. This can be the easiest way. And then when you just go to use a unit vector, just know that you're going to be 1 divided by the square root of 2, 1 divided by the square root of 2, and then your hypotenuse is 1. All right, so let's do that. So our vector BE is over 3 up 1. So we're going to be 3i plus 1j, and we're going to dot it with this unit vector. And this unit vector is, in the I direction we're going to be positive, in the j direction we're going to be negative, and the unit's going to be this. So we're going to be dotting it with a positive 1 square root of 2i minus 1 square root of 2j. So that is what we're going to be dotting. And the dot product is just the like terms multiplied, and then you're adding those. So I'm going to do 3 times this, and then 1 times this, or I should say that again, 3 times this plus, and then the j components, this times that, and I'm going to add those up. So we're going to have 3 square roots of 2 minus 1 square root of 2. And this is going to give us 2 square roots of 2, and that's going to be our distance. And is that going to be right? I feel like it may or may not be. But heck yeah, 2 square root of 2 is 1.4. 2 is bigger than that. And so, booyah. And if we wanted to rationalize this, we would just multiply by the square root of 2. And we would get 2 square roots of 2 divided by 2, which is just the square root of 2, which is 1.4142. So that is pretty close to our guess of 1.5. So I think we're just, we have a check on reality there. And there you go. That is the meat and potatoes of doing this method. And it doesn't require a lot of strokes of the pen. That's kind of cool. Like the setup's fairly simple, because now we know this perpendicular distance, and now we can get into the sum of the moments. We're going to sum the moments about E. Some of the moments about E are going to be 0, and the known forces are everything around this L, and we know the distance away, from there, and we know this perpendicular distance. So S2, if we start at E, put our thumb up into the air, and sweep our fingers in the direction of S2, or actually first, push your fingers in the direction towards S2, and then sweep your fingers with your right hand. This is going to be a positive moment, and we're going to have S2. So we're going to have that perpendicular distance is the square root of 2. Alright, I guess I just have to say, for whatever reason, because I've done this problem a few times, I don't want to look at my notes or anything, but it just feels like I messed up somewhere. But who cares? If we did, we can always go back and double check our answer. Alright, so we have the sum of the moments about E. We did this. We have a positive moment with S2. And just notice that S2 is our only variable. And if we know the perpendicular distance, it's just real simple. We have S2, and then we're going to multiply it by that square root of 2. That's our distance over to S2. So we have S2 square root of 2. Now starting from E, we're going to go over to these known forces. This 45 is going to have a component, this direction, and a component down. And then this L is also just going to have a component down. So we have 3 components. If this is up 1, oh, and I think the other thing is we needed to know, So if this is our 0, 0, this is, this part right here is going to be a distance of 5, 1/2. Cool. And this is 3, 1/2. So this vertical distance right here is just a half. So from E to this vector, we have a half. And it's going to be a negative moment. So we have negative 1/2. And then we have the magnitude of this vector, which this is a 45. So again, we have 1, 1, square root of 2. This is probably the fastest way to do this because I have the Pythagorean's theorem. 1 squared plus 1 squared is 2. So, and then this hypotenuse is the square root of that, square root of 2. But again, you can write it like, you can always just say, hey, this is 1 and this is 1, this is square root of 2, but instead of writing it here, might as well just write it like this. And then you just have your unit vector ready to go. And then this component is going to be, so we have 1 divided by the square root of 2L, that's going to be the component in that direction. So we have 1 divided by the square root of 2L for this component. Okay, now moving on to these. The distance over is a distance of 2. The moment is going to be negative for both of those. So we have negative 2. This component's 1 divided by the square root of 2L, and then just L itself. So we have minus 2L. Okay, hell yeah, and this is equal to 0. Now I have S2 on this side, and I want to solve for S2. I need to get these three things over to that side, and then divide them by the square root of 2. I'm going to do that in one step. A lot of math's kind of like juggling, and this ain't bad. You know, all these are just going to be positive over there. You can imagine that. And then we're just going to divide by the square root of 2. So when we do that, when we divide this by the square root of 2, it's just going to be a square root of 2 times square root of 2. It's just going to be a 2. So this one's going to be negative 1/4 L. This is going to be a 2 on the bottom after we divide by the square root of 2. 2 on the top. So this is just going to be negative L. And then we'll have 2 divided by, or minus 2 divided by the square root of 2L. Hell yeah. And now this is going to be equal to 0. So now we can simplify these. I can say this is going to be 4 divided by 4. So it's like negative 1/4 minus 4/4 is negative 5/4. Cool. And oh, and I already forgot. I tried to do 2 steps at once and I messed up. I needed to move these over. So these are all going to be positive answers. Okay, so now I have 1/4 plus 4/4 is going to give me 5/4. And I need to rationalize this one, so I just multiply top and bottom by the square root of 2. Alright, so we're going to do this probably in a couple steps. So we're going to have 5/4 L. And then we're going to have plus, this is going to be 2 divided by 2. So this is just the square root of 2L. Okay, now this has a denominator of 4. This has a denominator of 1. So I need to multiply both the top and bottom by 4. And now I can add these up. And the other, kind of half step is that they're in the answer, they're kind of putting this thing in front. You know what I mean? So I'm just going to rewrite this. S2 is 4 square roots of 2 divided by 4L plus 5/4 L. And now I'm going to get that final answer of, we're going to have 4 square roots of 2 plus 5 divided by 4L. And yeah, it was just fascinating going through this one, like thinking I made a mistake. I swear, like, it seemed too simple, but no, we got the right answer. And yeah, this was probably the fastest, the least strokes of the pen to get the answer. So I'm pretty impressed with that. And I think it was way more useful, kind of like going through it, instead of just having this sheet of paper and then talking my way through it. But hell yeah, so we got S2, and that's going to be, and it's in tension, because we have a positive on this, our arrow was correct. And alright, so we're just going to do one more, and that's going to be S1, and booyah. So thanks for joining me on this one, and that's a video.